Okay, I think I've closed the other window, so I won't hear myself talking back for once, which is good. Okay, so welcome everyone, and thank you for joining our last seminar of the semester. We've got the pleasure today of hearing from Kiyoshi Masui, who's a cosmologist currently based at MIT, whose research spans theory, data analysis, observations, and instrumentation, so a very, very wide range. And he's an expert on the large-scale structure of the universe, as well as observations of the structure at radio wavelengths. So Kiyo completed his PhD at the University of Toronto on 21 centimeter intensity mapping before moving to the University of British Columbia for several years, first as a postdoc fellow, then a research scholar, and then a Canadian National Fellow, before moving to MIT as an assistant professor. And today he'll be talking to us about a synoptic view of fast radio bursts with CHIME. So Kiyo, thank you very much again for agreeing to speak to us, and it's all yours when you're ready.
Great. Okay, and everyone can see my slides, I think. Okay, good. And let me just arrange my windows just a bit so I can see your faces. Good, and I can also see the chat. So if you have any questions, feel free to just post them in the chat and I will try to get to them. Okay, oh, and that's not even my title slide. Okay, so super. Okay, thank you. So I'm going to tell you about fast radio bursts and how a new generation of digitally driven instruments like the CHIME telescope that I'm showing here on my title slide give us the first opportunity to get this really sort of synoptic all sky view of what this sort of mysterious phenomenon of fast radio bursts are. So to start off, what are fast radio bursts? So fast radio bursts are they're defined to be just single radio flashes that are very brief. They're typically milliseconds in duration. They're broadband, so they've been observed over a wide range of frequencies, down to a few hundred megahertz, up to 5 gigahertz, and then each individual burst is typically it fills the bandwidth of the instrument that detects it. Typically something like an octave of bandwidth. They are bright. They are typically something like 1 to 100 Janskys. So Jansky is a unit of flux that that radio astronomers use. It's the sort of the typical brightness of a radio source in the sky for in the radio. So depending on what frequency you're observing at, there may be one Jansky radio galaxy per something like square degree, maybe a few square degrees on the sky. So a typical radio galaxy would be a Jansky, and critically they're of unknown origin. They're typically very poorly localized, and so we don't really have a very good, very precise view of where they're coming from. The instruments that are really good at finding these typically are able to localize them to a few arc minutes, maybe a degree precision. They're almost certainly related to neutron stars in some way, shape, or form, and that just comes from the short time scales, right? So only objects smaller than a light millisecond can make a millisecond long flash, and that's just because if the emission region was bigger than a light millisecond, you'd have a geometric broadening of the signal, and the flash would appear to us to be longer than a millisecond, and so it can't be bigger than a light millisecond. A light millisecond is about 300 kilometers. And so the only objects that we can think of that are smaller than 300 kilometers, but have the energy reservoirs required to make these fast radio bursts are neutron stars. There are, of course, more exotic explanations, but neutron stars are the sort of the normal astrophysics explanation. That being said, how or why neutron stars would create these bursts is a complete mystery. Perhaps the defining feature of fast radio bursts is that they're highly dispersed. So it turns out that at radio wavelengths, the radio waves do not travel they do not travel the speed of light, and that's because the universe is filled with very diffuse ionized plasma, and in a plasma, that plasma has a refractive index for radio waves, meaning that light travels just a little bit slower, and that's actually dispersive, meaning that different wavelengths of light travel at different speeds. So the shorter wavelengths, the bluer light, travels a little bit faster than the longer wavelengths, the redder light, and that means as it propagates through the gas, say the ISM or the IgM, you get this delay of the longer wavelengths with respect to the shorter wavelengths, meaning that we observe them earlier at higher frequencies than we do at lower frequencies. That delay constant of proportionality is called the dispersion measure, which turns out to be proportional just to the line integral of the density of plasma, the path integral of the density of plasma. So it's really just the column density of free electrons is what determines how much delay there is. And so, every single fast radio burst, by observing this delay, you get a measurement of how many electrons were along the line of sight. The units we usually quote this in is in parsecs per centimeter square cubed, right? So that's actually an area density, column density, but these give sort of the convenient units because your path is going to be most conveniently measured in parsecs, and your density is most conveniently measured in inverse centimeters cubed. Okay, so this is what that looks like in real data. So here I'm showing data from the Green Bank telescope between 700 and 900 megahertz, and as a function of time on the horizontal axis here. And the color scale is just how much power is being received by this telescope, by the Green Bank telescope here. And what you can see is that if you look, if we looked at a single frequency as a function of time, okay, you see kind of noise, and then blip, a brief flash. It's about a millisecond long, right here, and then more noise. Okay, and so that flash lasts about a millisecond, but that flash arrives at different times at different frequencies, right? And this is that dispersive delay that I was talking about. Okay, and so by measuring how the arrival time changes as a function of frequency, we get this dispersion measure, and thus this measure of the electron column density. So dispersion, it gives us this total column of intervening free electrons, and that actually can be used as a distance measure, right? So in pulsar astronomy, we also observe dispersion. Pulsars also produce sort of millisecond duration flashes of radio light, but very, very regular ones. And so we can observe that dispersion there, and that's actually used as a tool in pulsar astronomy to observe to measure distances, right? So if you have a model for where the plasma is, where the free electrons are everywhere in the galaxy, then if I look in some, and that one such model is here, okay, showing us here in the galactic center there, and these contours show in the galactic plane how much dispersion measure you get between us and a source, depending on where it is in the plane of the galaxy, right? And so if we observe a pulsar with a dispersion measure of let's say 200 coming from this direction, then we know it's about here in the galaxy. It gives us an estimate of where it is in the galaxy, right? And so that gives us that's regularly used as a distance measure. The thing that makes fast radio bursts really special is that the dispersion measure that we see in them is typically much higher than pulsars, and they're not observed to be in the galactic plane. They're typically observed at high galactic latitudes. And so if, along those lines of sight, if you just ask, how many free electrons are there in the Milky Way, you find that our models don't have enough electrons to give us the dispersion measures we see, right? the origin of that, they're so highly dispersed. The origin of those bursts has to be beyond the Milky Way. There just there isn't enough plasma locally to provide that dispersion. And then the thing is that as you get outside the Milky Way, the plasma becomes very, very diffuse, right? The ISM is very diffuse, but the IGM is much more diffuse than the ISM. And so once you get outside the Milky Way, it's very, very hard to accumulate dispersion measure. It's very, very hard to accumulate electron column density. And so in order to get the very high column densities that we observe, it turns out you have to go to cosmological distances, okay? And so suddenly you're in the regime where these objects aren't in our galaxy. They're not even in the galactic neighborhood, right, or the local universe. They are at cosmological distances. And in fact, a handful of these bursts have been localized with interferometers, and we've identified their host galaxies. And those host galaxies have been in the range of redshift 0.03 to redshift 0.7. Okay, so truly at cosmological distances. And that redshift actually, which is another distance measure, of course, matches the distance that we would have inferred from the dispersion measure to about 10%, right? And so this dispersion measure that we see is in fact a decent proxy for how far away these bursts are, implying that they are at cosmological distances. The other sort of striking thing about fast radio bursts is their abundance. So FRBs. So in the period, the first decade since they were first observed, from 2007 to 2017, something like 50 fast radio bursts were discovered and published in the literature. And so that doesn't seem like a lot, but that number is entirely dictated by the field of view of the radio telescopes that could see them, and were searching for them. And so we were only surveying a very tiny fraction of the sky at a time. And because they're so brief, you have to be looking at exactly the right place at the right time. So if you extrapolate that 50 that we saw to how much we were looking, you conclude that something like 3,000 of these things happen over the full sky every day. So they're just very, very abundant. So I like to show this in an animation. There's nothing super deep about this. It's just a map with some flashes painted on, but it gives you, it's just meant to put you in the right headspace of what I'm talking about. If you could see the whole radio sky in the radio, with your eyes, and could see the whole thing, these things would be happening all over the place, right? Every minute or two, maybe a few seconds, you would see a radio flash. This is a striking feature of the radio sky, where flashes are coming from random directions all over the sky. Each flash happens once and doesn't repeat, and for the most part doesn't repeat. Okay, so I think I've laid out the mystery there, and so how do we make progress in this field to understand what these things are? And I think maybe the best way forward to do that is to get a larger sample, right? So 50 FRBs discovered over a decade just isn't going to cut it. If we really want to study this phenomena, we need to discover them at higher rates so that we can sort of learn something, learn more about them. And so so I said before, the reason we only discovered 50 is because we can only search a very small parts of the sky for these things at any given time. And so how do we overcome that limitation? How do you make an instrument that's able to see a large swath of the sky at once? Okay. So the question is, how do I make a wide field but very sensitive radio telescope? And so one way to think about this, to motivate this, is to think about telescope design, right? So how does a radio telescope work? Well, it works the same way as an optical telescope, or basically any other telescope, especially these single dish ones, right? You have a big mirror. That's what this thing is here. and that mirror has two jobs, right? That mirror needs to collect light over a very large area, right? So that you are sensitive to light coming from far away, right? But can't just collect that light. It also has to focus that light, right? The geometry of this mirror has to be just so that rays coming in from a specific direction, they bounce off the mirror and they add up together. They come together out of focus with just the right phase delays, such that this radiation adds up constructively at the focus, right? So that gives us amplification of the light, but it also gives us spatial information because this geometry, these rays only add up in phase at the focus, at this one place in the focus for light coming from a certain direction. So it gives us, and light coming from another direction, it doesn't add up in phase here. It adds up in phase somewhere else, where you're not sampling the electric field, right? Where you're not measuring the electric field. So this mirror and what the telescope's doing is collecting that in phase. Another way that you might want to design a radio telescope is just by carpeting the ground with antennas, right? So if I just want to collect a lot of light, I could do that with a big mirror, or I could just carpet the ground with antennas and collect all that light. And that would do one of the jobs of that mirror, right? It would collect all that light, but it wouldn't necessarily add it up. It wouldn't necessarily focus that light, right? However, what you can do is you can digitize the signals that all that light that you observe, and you can focus it digitally. Okay, and that's what this new generation of radio telescopes is doing, right? Is instead of using optics to focus our light, we actually just collect the light coming from over a large area. We digitize it and we focus it using digital signal processing. So this has a couple big advantages. It has the advantage. It has the advantage that you can point your telescope. You get to choose exactly how you focus your light, right? So you get to you can choose for that light to be in focus for if it's coming from a certain direction, right? So I can point my telescope, this telescope, anywhere I want with no moving parts, right? I just change exactly how I do this focusing. But the big advantage is that I can point it everywhere simultaneously, right? I can focus it in as many different ways as I want, all at the same time, just by duplicating my software, right? And so with no moving parts, I can both, I can both point my telescope everywhere, but I can also point it everywhere simultaneously and see sort of a broad swath of the sky at once. So without further ado, let me introduce the actual telescope that I work on, which is the Canadian Hydrogen Intensity Mapping Experiment, or CHIME. Okay, so CHIME is actually a hybrid between both these approaches. Okay, so it does have a big mirror, right? It actually has several mirrors, right? But those mirrors are these cylindrical half-pipe looking mirrors, and they only focus the light in the east-west direction. Okay, that means that any antenna that we have at the focus here, it sees a broad swath of the sky, right? It's focused in the east-west direction, so we have the extent is narrow. The part of the sky it sees is narrow in the east-west direction, but it's not focused north-south, so we see a broad swath of the sky in the north-south direction. And then we rely on digital signal processing to focus the light in the north-south direction, and also combine the light from these four mirrors that we have to get extra focusing in the east-west direction, right? And that gives us this grid of beams, grid of pixels that is able to see a large swath of the sky. Now, CHIME has no moving parts, so it always points straight up. So it's always observing the meridian, north to south here. However, because the sky rotates, it surveys the entire northern sky once per day. Just to give you some vital statistics of the telescope, so it's located at the Dominion Radio Astrophysical Observatory in Penticton, British Columbia. It covers the 400 to 800 megahertz band. It has roughly an equivalent aperture that's something like 80 meters by 80 meters, so a pretty large aperture by radio telescope standards. So that gives us, a diffraction limited resolution of something like 0.4 degrees. But then the really special thing about it is that it sees a large swath, 120 square degrees of the sky simultaneously. So it has a very large field of view. But this telescope that I'm showing here, that's only part of the telescope because it's the heart and soul of it really is the digital signal processing that makes it tick. We've instrumented those mirrors with 2,048 antennas, each with their own analog digital converter that sits on 128 separate FPGA boards. So this is basically a computer cluster in itself, just to digitize all that data. And that produces 6.7 terabits of data, of measurements of the electric field, baseband data, per second. Okay. Then it's then sent. That data is then sent to our correlator, which is a 256 node cluster. Each one of these nodes has 4 GPUs. So that's what's shown in the background here. This is half of our correlator, 128 nodes. And they have those, that correlator has to do 6.7 peta operations every second to correlate the data to focus that light. So that turns out to be the biggest digital correlator in the world. It's about 6 times more computational power than the ALMA correlator, which would be the runner-up. And then that data is then sent to another cluster for the FRB instrument. That's a 128 node CPU-based cluster that searches the data, the resultant data streams for fast radio bursts. So CHIME was commissioned in 2000. It started commissioning in 2018. It started, doing science then, and I don't have time to go through sort of all the results that we've had since then. I'll just give you a couple of highlights. Basically, right away when we turned on in July of 2018, we started discovering fast radio bursts. We had sort of the lowest frequency fast radio bursts that had been observed. So before we turned on, no one had ever observed a fast radio burst at 400 megahertz. We discovered a subpopulation of fast radio sources that emit repeating fast radio bursts. So prior to CHIME operating, there had been one source that was known to emit multiple fast radio bursts, one out of something, out of a few dozen known sources. But it wasn't known if there was a substantial population of these or if that was some sort of special event, right? But now with CHIME's very wide field of view and its ability to serve the whole sky and visit the same spots of the sky with regular cadence, we're discovering that these sources that emit repeat bursts, they're fairly common in the universe, right? We've discovered dozens of them now. One of these repeating sources was localized to a nearby star forming region and a star forming galaxy, which helped for understanding what environments and what sorts of galaxies these FRB's sources come from, and that same source was observed was a repeater, and it was observed to be active on a 16-day period. So that means that particular source, we would see fast radio bursts from it and we'd see them in a couple-day window typically. So if we saw a burst, then we'd see it. We're likely to see another one within a few days. But then there would be this 12-day period where there were no bursts emitted at all, and then the cycle would repeat. So there was this 16-day activity a period where, for 4 days of that 16, the source emitted bursts. And then finally, we discovered, saw one fast radio burst that was emitted from a galactic source. So all other FRBs had been emitted by extragalactic or extragalactic in origin. We saw one that came from a galactic magnetar. That was identified in the X-rays. So, taking, sort of these results and other observational results from the community together, this is starting to paint a picture about what the origin of fast radio bursts are, right? And all these clues are pointing to that the sources that are emitting them are magnetars. Okay, so what are magnetars? So magnetars are very young neutron stars, and their defining feature is that their emission is power is still very strong magnetic fields. So these are the highest magnetic field, most highly magnetized objects that we know in the universe. They tip and they're typically bright in the X-ray, although some of them have radio emission as well. And that energy, that reservoir of energy, is actually stored in those very strong magnetic fields. So magnetars are favored as sources because of one, this direct association, right? We saw a fast radio burst from our own galaxy that was coming from a magnetar. So at least some fraction of FRBs have to be coming from magnetars, because we have at least one example. But but more broadly speaking, the whole, many people had always suspected magnetars of being the source of these things because of, the energetics, right? Magnetars have a large energy reservoir that they can draw on to produce these bursts. The short timescales, right? So we already said that they had to be were probably coming from neutron stars, right? And magnetars are a subclass of neutron stars, so that fits. We also seem to see, with a handful of FRBs that we've localized, there seems to be an association with star formation. So magnetars are very young neutron stars, so they're typically associated with star formation, and so that fits. And then we have this observation of periodic activity. We don't quite know how that fits in the model. It fits into this picture, but it could have something to do with a binary orbit or with precession or something of that sort. So these observations, this fact that we're starting to see, large populations of fast radio bursts and see, lots of, and have a large discovery space of finding the sources that will give us the best clues, are starting to paint this picture, solve this mystery of where the fast radio bursts are coming from, and the clues are pointing towards that magnetars are the culprit. Okay, so that was a quick survey of what of our results to date, but what I really want to talk about is population studies, right? So all those results I mentioned, those are all studies of individual sources. But the real power of CHIME is not, it's both the ability to detect lots of sources and therefore find the interesting ones that give us clues, but also just to see many, many sources and allow us to study these things as a population as a whole, right? And so this is, and where we do this is the upcoming CHIME FRB catalog. So the vital statistics of the catalog is this is the first 535 FRBs that we detected, and these were detected in our first year of operations, ending in 2019. It includes 61 bursts. 61 of those 535 come from 18 sources that are known to repeating sources, but all the others are apparent one-offs. We don't know if they're repeaters or not, but we haven't seen them repeat yet. And then the key thing about this catalog is that we have measurements of many properties of each of these fast radio bursts, and and the thing that's going to let us study them from a population point of view is that we're measuring the same properties for each burst, and we're measuring them all in the same way. So those properties are things like the dispersion measure, the temporal width, the spectral index, and a number of, the brightness, signal noise, and a number of other properties, right? And that's really what's going to let us study these things as a population. Okay, so what can you do with a large sample of, the biggest ever sample of fast radio bursts? So the first thing you can do is compare, these 61 bursts to all the other bursts that we saw, and ask, is there something special about repeating sources? So the comparison of repeaters and one-off bursts. Okay, and so let's dive down into the data a bit. So here are two fast radio bursts. The data from two fast radio bursts. So this is similar to what I showed before in one of my early slides, except here you don't see any of that dispersion delay, right? This millisecond flash happens at the same time at each frequency, and that's because the dispersion delay has been taken out here. So we've just removed the dispersion delay so you can really zoom in and see the morphology of these two bursts. And here are two fast radio bursts that are very different, right? So this one seems to be very broadband, right? I can see signal all the way up here at 800 megahertz. I can also see signal down here, it's smudgier at 400 megahertz, okay? And it seems to be quite narrow, right? This is only a few milliseconds long. The duration is longer at low frequencies than at high frequencies. That's actually expected because of scattering from structure in the line of sight plasma. Right, but that's in stark contrast with this burst here, right? So this burst, it does not fill the band, right? We only see this burst from 600 megahertz and up. Its duration is much, much longer. It's something like 30, 40 milliseconds, right? And it seems to have a lot of substructure, right? There seems to be a little subburst here, a subburst here, and oh, sorry, you can't see my pointer. I'm pointing at the wrong place. There's a subburst here, a subburst here, and a subburst here, right? And those, so there's the substructure, and each one seems to be centered at a different frequency. Okay, so that's two. That shows the diversity of the properties that you can see in fast radio bursts. And then we ask, okay, is there any difference in these properties, this observed morphology, between repeating bursts and ones that have not been observed to repeat yet? And so we can measure properties in a standard way. So let's say we measure the bandwidth, right? So this burst would have a bandwidth of 400 megahertz. This burst would have a bandwidth of maybe 200, maybe 150 megahertz, okay? And we can also measure the duration, right? So this burst would have a duration of maybe 5 milliseconds, and this one would be something like 30, okay? And we can just, and we can plot that separately for bursts that have been observed to repeat. Those are in blue, and then and the ones that have not yet been observed to repeat. So what we call one-offs. And we see that their distributions are starkly different, right? One-off events tend to look like this event on the left, right? Broadband, very narrow in time. And repeat bursts tend to look like this one on the right, smaller bandwidths and more extended in time, okay? So that's an argument that it might be some real difference between things that we've seen to repeat and ones that we haven't, right? The repeaters could be a different population even, right? It's suggestive that the repeaters are a different population, that these might be coming from different astrophysical phenomena, right? And that's evidence against the interpretation that all fast radio burst sources repeat, and the ones that are one-offs we just haven't seen repeat yet. So that's sort of a hint that we might be looking at multiple populations. Okay, and then the next thing I want to talk about is sort of absolute population characterization. So comparisons, what I talked about before were comparison of two different subpopulations, and that turns out to be fairly easy. And the reason that's easy is because they're coming from the same survey and they have the same selection effects, right? But anytime you try to make an absolute measurement of a population, you have to worry about selection biases, all right? And actually this field is absolutely plagued by selection biases. And it turns out these biases are so strong that very simple questions that you might ask, right? It's like, how are the observed what's the brightness distribution of FRBs? how many bright FRBs do we see compared to dim FRBs? Or, how many FRBs are there in the sky, right? Over the whole sky, above some brightness, how many FRBs, what is the rate of FRBs? These are very basic questions you can ask. And it turns out these are really, really, really hard to answer because the selection biases are so strong that you have to really have control of them in order to answer these questions. Okay, so let's, I want to do a sort of a deep dive into one of these questions, and this is the brightness distribution. Okay, so let's say you have some flux threshold, F min, above which you can detect an FRB. And we ask, how does the number of FRBs we detect depend on that threshold, right? So at lower thresholds, we expect to see more FRBs, right? And this is expected to be a power law, and we're going to give that power law index for this cumulative distribution a name, and that's going to be alpha. Okay, and alpha is supposed can have, so there's one magical value of alpha that you might expect, and that's -3 halves. Okay, that's if the sources, if in a Euclidean universe where you have uniform density of sources, and where evolution aren't important, and the expansion of the universe isn't important. Okay, in that case, if I don't have to worry cosmology, and flux I squared, right? And so the maximum distance I see a given burst out to goes as 1 over square root of the flux, right? And of course, the total number of sources I can observe goes as the volume, right? And you work all this through, you get that the number of sources I see should go as my sensitivity, my flux threshold, to -3 halves power. Okay. So that's basically the expectation, right? This expectation of alpha equals -3 halves will be broken by cosmology, right? It'll be broken by the expansion of the universe and by source evolution, right? If the sources themselves change their abundance over cosmic time, we'll break that. Okay. But for if the population lives at a redshift less than 1/2, these should be sort of minor effects, and we expect to measure this -3 halves power. Okay, and it turns out the literature values, the literature measurements of this power law index have been just spectacularly discrepant, right? So we've had measurements that say that this is very, very flat, goes to the right at basically completely flat. We've had something at with alpha -1, very steep measurements, alpha -2.2, right? So lots and lots of different measurements, all with error bars that are just very discrepant with each other, right? None of these measurements can be, this discrepancy can come from just the statistical uncertainty. Okay. And so the reason for this is because the selection effects are just very, very, very hard to control, right? And so you need to do a really good job of calibrating these selection effects. So how do we do this in CHIME? So what we did is we created a synthetic signal injections pipeline. So here's a schematic for the pipeline over here. You don't have to understand it. Just know that what we do is we inject synthetic signals. We add signals into our data in real time, and see if we detect those signals, right? And so that we can inject thousands and thousands, and actually even millions of these fake bursts into our data stream, and we can figure out which ones we detect and which ones we don't, as a function of all the properties, as a function of how bright they are, as a function of their dispersion measure, of their width, their bandwidth, all these things. Okay, so this is work that was led by a student at the system that was developed by a student at McGill, Marcus Merrifield. Okay, so if you use this system to calibrate these selection effects, and then you can analyze our catalog. And this is work that I did with my graduate student Caitlin Shin. And this is showing MC-MC chains for the fits that we get after compensating for selection effects. Okay, with alpha on the horizontal axis and the total rate on the vertical axis. This is the rate above affluence of 5 Jansky milliseconds. And we see that we get something consistent with this alpha equals -3 halves. Okay, with error bars that are of order 0.1, right? So smaller error bars than before. That shouldn't surprise you because we have more bursts than any other survey, okay? And we also measure the overall rate to be something like 1,000 FRBs over the full sky per day above this fluence threshold of 5 Jansky milliseconds. Okay, but we can go further than this. We can ask, okay, we can ask how this depends on distance, right? So this expectation of alpha equals -3/2, that holds only if you include sources at all distances, right? Remember, we had this argument here, right? That said, if I observe all distances, if I integrate over distance, then I should get this, this scaling. But remember, we have a separate proxy for distance. We have the dispersion measure, right? And so if we subdivide the population into nearby bursts, ones with low dispersion measure, and far away bursts, ones with high dispersion measure, we should, you know, we don't need to measure a -3/2, even if the universe was perfectly Euclidean, even if cosmology wasn't important. So we did this, right? And so for the high DM bursts, we observe a much steeper brightness distribution, and for the for the far away burst, we observe a much steeper luminosity brightness distribution, and the nearby burst we observe a shallower brightness distribution, like that. Okay, and so those I want to argue that this is actually exactly what you expect to see. All right, and so here's a cartoon of what the luminosity function could look like. Okay, so let's say the intrinsic. So remember, I'm not talking about, you know, this isn't a measurement of the luminosity function. It's a measurement of the observed distribution, right? Of the brightness distribution, not the intrinsic luminosity function, right? So this brightness distribution is the luminosity function, is the observed brightness of the luminosity with over the distance squared, right? If the intrinsic luminosity looks something like this, right? And in particular, it has to be sort of concave down. And the reason it has to be concave down is if it isn't concave down, then then the total energy in fast radio bursts in the universe will diverge, right? If I don't want to integrate, the total energy in fast radio bursts is like the energy, the luminosity distance times the energy. It's the integral of that. And if I don't want to have that diverge at low energy or at high energy, then I need a concave luminosity distribution. That makes sense, right? You can't have an infinite number of sources with either very low luminosity or high luminosity. Right, and so if it's concave like this, then and I also have a distance proxy, then if I look at far off sources, then I'm preferentially going to sample sources that are high energy, right? And if I look at nearby sources, I'm preferentially going to look at sources that are at low energy, right? Because I can see, there's more of them, right? And I'm expecting to see the shallower distribution of sources at nearby than I see far away if this luminosity distribution is concave, as it has to be, right? And that's exactly what we see. So what I would argue is that we are now seeing, evidence of the shape of the luminosity function in our brightness distribution, right? Even though if in the Euclidean case, no matter what the luminosity distribution is, you have to measure this, alpha equals -3/2 index. But once you subdivide by distance or dispersion measure, you can start to sample the luminosity distribution, the luminosity function. Okay, so that's what I had to say about the population. Now I just want to spend a couple minutes talking about the next instrument that we're working on. And that's the CHIME VLBI outriggers project. So CHIME's big weakness, remember I said it's really good at finding fast radio bursts because it's very sensitive and sees a large field of view of the sky. What it's really bad at is localizing those fast radio bursts. right? And so if you ask, what's the localization of a typical compact radio telescope, like Arecibo, right? Actually, Arecibo is quite a bit bigger than CHIME, and so actually CHIME's localization uncertainty, it would be like several times bigger than this, and you'll notice that localization region is bigger than the Hubble deep field image, right? And so when we see a fast radio burst, we don't know where it is, where we only know where it is to some large region that contains just thousands and thousands of galaxies. So it's completely impossible for us to tell you which galaxy a fast radio burst came from without support from another telescope, like the VLA or EVN or something. Okay, and so that means we basically, it's very rare for us to figure out what galaxy a fast radio burst came from. So we want to fix this, and we want to have precision localization of the FRBs that we're seeing. And the way we're going to do this is we're going to build what are called outrigger telescopes. So those are small copies of CHIME. Each one is about 1/8 the collecting area of CHIME, but they're located very far away from CHIMEs, of order 3,000 kilometers away. And we'll roll so that they're observing like this. So that they're observing the same patch of sky as CHIME is observing. Okay, and they'll have nearly identical, optical. Otherwise, other than the fact that they're smaller, they'll be nearly identical optically, and their analog systems and their digital systems. And these are the two sites that we've been working on for locating them. And in fact, we are actually already preparing sites. Construction has basically begun at Allenby, which is about 100 kilometers from CHIME over here. GBO, the GBO site is also currently being prepared, so we're getting ready to break that ground there. And these telescopes, we're going to use them in tandem with CHIME to localize FRB using very long baseline interferometry. So the goal of this project is just to localize every single CHIME detected FRB, which will be thousands ultimately, to better than 50 milliarc second precision. The reason this is really hard is because this is kind of an unprecedented technique in that we don't know where or when our VLBI target is, right? So we're doing VLBI on sources that we don't know where they are going to be beforehand, okay? And one of the things that makes this hard is just the data rate, okay? So there's a fundamental scaling of the data rate, of the baseband data rate. So for VLBI, you need phase coherent observations, okay? Meaning that you need to, so that's what we call the baseband data. And there's a fundamental scaling of that baseband data rate, which is that it goes to the field of view, which is very large for CHIME, times the collecting area, which is fairly big for CHIME. We have a lot of bandwidth. We want to keep a reasonable bit depth. And so that turns out to be almost 7 terabits of data per second for CHIME, which is something like 1% the total average world in internet bandwidth. So it's a lot, right? And then for an outrigger, that works out to be 800 gigabits per second, which is smaller but still gigantic, right? So let's compare that to an EHD station, which is like probably one of the most data intensive VLBI recorders, systems in the world, and we're a factor of 10 bigger than that for an outrigger and a factor of 100 bigger than that for CHIME itself, right? And so everyone has seen these pictures of these giant banks of drives that EHD has to ship around, right? So we just can't possibly record all that data, right? And yet we never know when an FRB is going to happen, right? And so if we're trying to observe FRBs, we just kind of have to record this data at all times because it could the source we're looking for could happen anywhere at any time. Right? And that's just very challenging. So what we've invented is a triggered baseband recording system, right? So how this works is we have this baseband data. So these are the coherent measurements of the electric field that are produced by the telescope. That's before we do this digital signal processing to focus the light digitally. And that goes into the correlator, the beamformer, right? Which does that digital focusing stage. And then it comes out as intensity. So this is non-phase coherent data. And that's the data that gets searched for fast radio bursts. Okay. However, we also tee off this data and we hold it in a 40-second ring buffer. So we can't afford to record 6.6 terabits per second, but we can afford to hold on to it for 40 seconds, not much longer than that. And then when we produce triggers, when we detect a fast radio burst, then we can write that data to disk. Okay. And this is the data that we need to do VLBI. Okay. And then so we're going to replicate that system at the outrigger system, at the outrigger stations, right? But at the outriggers, you don't need to focus the data. You don't need to do the beamforming. You also don't need to search for FRBs. CHIME will find the FRBs. We're just going to send the triggers over the internet, save that baseband data to disk, and that's going to that will give us the data we need to do VLBI on FRBs. So this might all sound like a very lofty goal, right? To do this wide field, blind search in VLBI. And it is. It's never been done before, but we think we can do it. And one of the reasons we think we can do it is because we've already demonstrated most of the main key technologies we need with the CHIME Pathfinder. So it turns out before we built the CHIME telescope, we built a small version of CHIME over here at DRAO. That's called the CHIME Pathfinder. It's about 1/8 the size of CHIME. That was a technology demonstrator and a prototype for CHIME. We've repurposed it by instrumenting it as a VLBI outrigger. So we've changed much of the digital electronics to do just this. Now the baseline isn't very long. It's only 380 meter baseline, so it's not going to give us very precise localizations, but it will let us test this triggering and calibration methods and a number of other things. And so we did this. My lab, my graduate student, along with a postdoc working at MIT, that embarked on a campaign to prototype all of this. And we've demonstrated this triggering and recording system. We've demonstrated that we can correlate the data on separately clocked telescopes, right? So here's that data. This is a visibility, and showing a fringe, right? And there you can see the FRB right here, right? And you can see it both in the real and imaginary part. So this is basically a fringe on an FRB. And we're also using this to test, these wide field calibration techniques that we're going to need to really precisely localize. So the end result of this program is going to be thousands of FRBs, every one of which will have a dispersion measure, will have the localizations to 50 milliarc seconds or better. That's going to yield host galaxies, and it's going to we'll eventually get redshifts for all those host galaxies. Okay. And that's something that really excites me, because that's going to transition fast radio bursts from being a study of just these high energy astrophysical phenomena to a probe of cosmology and the large scale structure of the universe, right? So remember, dispersion gives you a measure of the line of sight of the plasma along the line of sight, right? So it gives you the plasma column density, right? And if you have dispersion and redshifts, the distance and the localizations of all of these, you can start to figure out in 3D where is all the plasma in the universe. You can make 3D maps of the large scale distribution of gas. Okay, so this has a number of potential applications. We can figure out exactly where the missing baryons are. So that's basically saying we can measure the electron power spectrum, the plasma power spectrum, on intermediate scales. We can use that to understand feedback processes and galaxy formation, right? How much is the gas heated and where is it relative to the clusters and filaments? And then ultimately we want to use this for cosmology and to study the large scale structure of the universe. Okay, so in conclusion, so CHIME's digital design makes it basically the most powerful machine on the planet for discovering fast radio bursts. And that's yielding a bunch of new clues about the nature of both these repeating sources and there's the distinction from non-repeaters. We have now have a large catalog of fast radio bursts that provides the first large sample with known selection biases for measuring properties of the population. And then we are currently developing these VLBI outrigger telescopes that will yield thousands and thousands of localizations of fast radio bursts. So ultimately, we're going to get FRBs, thousands of FRBs with dispersion measures, with localizations, with redshifts, and that's going to be a new tool for mapping out the large-scale structure of the plasma in the universe. Thank you very much.
Wow, Kia, that's a lot of very cool science. Thanks very much. Yeah, it was great. I imagine there will, I mean, a round of applause is always kind of hard virtually, but it would be thunderous, I think, in person. So I imagine there'll be quite a few questions. So I suggest we if I can bring up participants. Yeah, does anyone have any questions to start off? Phil, I can see your hands up.
Hi, Kia. Thanks for a really nice talk. Yeah, this, like Ed said, this is super cool. But you know that anyway. So, I was kind of wondering a little bit about polarization and whether that's an option with the VLBI setup. Are you able to do much with polarization, or how does the calibration for that work as well?
Absolutely. So I'll go back to this system. So here in the beamform intensity, we don't actually keep polarization information here because we just can't afford to. The data rate from the correlator to the FRB search backend is too high. We can't afford the factor of 2. But actually, because they for FRB, we can go back and beamform this data offline, and we can do that with full polarization information. So we do actually have full polarimetric data on basically every FRB that we detect. Not the early ones, because it took us a while to get this system up and running, but for most of the recent ones. So we are actually doing a bunch of science with that. We have Faraday rotation measures for a bunch of FRBs. We're starting to publish that now. There's one publication from a student that I work with, Ryan McKinven, who's Brian Gensler's student in Toronto, showing all the details of how we calibrate the polarization, how we fit for the rotation measure, and what you actually end up doing is, instead of calibrating, it turns out the data is instead of doing polarization calibration, the data is not terribly calibrated already. There's a couple parameters that you need to fit for, which are like the relative delay between the X and Y feeds, but we can fit for that in our simultaneously with the Faraday rotation, and get that. Another one is like the relative gains of the X and Y feeds is another parameter we fit for in the study, and that's all described in Ryan's paper.
Great, thanks. I suppose you're at high enough frequencies that you don't have to worry about atmosphere or ionosphere stuff with the polarization. That's just not even. It's
small, but not. We ignore it right now. So our typical FRB has a rotation measure of a few hundred. A low one might be a rotation measure of 10. The ionosphere gives you a rotation measure of 0.1 to 1. So it's 1% on the total Faraday rotation we observe. It's subdominant.
Okay. Do you have to do any monitoring at each site for the VLBI outriggers, or it's not important enough to worry about?
Oh, for VLBI, it's a huge deal. Yeah. So for polarimetry, it's not that big of a deal. For VLBI, if we ignored it, it would dominate our error budget. So we have to because we have a very wide bandwidth. One thing we're going to do is just fit for it in the data, because the ionospheric delay is dispersive the same way as the normal DM is. And so we can see how it changes a function of frequency and fit it out. Excuse me. But we are also hoping just to use models and GPS monitoring to remove, say, 90% of the effect, and then it will be subdominant.
Neat. Thanks very much for that.
No problem.
Cool. Okay. Any other questions? Yeah, I think Chris, maybe. I'm not sure who was first out of Chris and Tessa. Maybe Chris, if you're ready.
Okay, yeah, hi, thanks for that really nice talk. So unless I missed it,
you didn't say a lot about the sort of physical processes that might be causing these bursts. I was wondering if you had any thoughts about that. I've heard of magnetic reconnection being used as one of the explanations, but this is not my area. So I was wondering if you had any thoughts about that.
Yeah, so that's just displaying my bias as someone that's trained as a cosmologist that have like all the high energy astrophysics phenomenology is hard for me to understand in general. But yeah, there are a number of models that work. There are these magnetic recombination having to do with star quakes and stuff like that. And on the magnetar, these on a magnetar, there are these shock models where you have an X-ray outburst that causes a shock through previously ejected material, and that causes a maser mechanism to create radio emission. There are a bunch of these models for getting the detailed sort of high energy astrophysics. I'm just not an expert in that part of it, and so I tend to veer away from it just because I'll inevitably get it horribly wrong. But yeah, I think there's now a vast literature on candidate models, and I don't think every once in a while there's an observation that favors one over the other, and then we typically get within a few months an observation that goes the other way, and I think they're still duking it out basically.
I'm sort of comparing to something I know a little bit more about, which is solar radio bursts, right? And so there we know there's different types. So from some solar flares we get some one type of radio emission, and from sort of the shocks accelerated by CMEs we get a different type. So do you think that it could be that these different processes are all happening, and that's what's giving you your different classes? Whether they're repeating or not repeating?
Yeah, I would definitely not rule that out. In fact, so there's just as a sort of total sociology side of things, right? There was a poll done at the last big FRB meeting the question was, are repeating FRBs a distinct class from non-repeating FRBs? And the community is basically split 50-50. So we just have, there's no consensus whatsoever. I would be very, I think it's certainly possible that there are distinct classes, at least distinct mechanisms, if not distinct, sort of sources.
Okay, thanks.
Yeah, Tessa.
Hi, so sort of a related question to Chris's then. So if it is true that these FRBs are not coming from a single population of object like magnetars, but instead are perhaps coming from different source populations, are they all likely to be things that neutron stars do on their own, in quotes, like a magnetar? Or is there any possible connection between FRBs and gravitational wave sources, for example, that's hypothesized?
I don't know of any models. Like very early on, there were models that had like neutron star collisions, right? Which would of course have associated gravitational wave emission. Now, after the repeating population was discovered, those models died because it's hard to get the same source merging neutron stars multiple times. Also, from a population point of view, there just weren't eject of them. And then there's also a lot of challenge of getting the radiation out without it being obstructed by the ejected material. And I think that's one of the biggest problems with the models, especially if you invoke multiple populations. In the previous two arguments about not having enough neutron stars, or the fact that we see repeats, those don't apply anymore if you thought there were multiple populations, because it can be an arbitrarily small fraction of the population. But then getting the radio emission out past the ejecta is still very, very, very challenging. So that's the one that comes to mind. I don't know if there is a very large diversity of models. I don't know the field in a complete enough way to tell you that there aren't other ones that involve gravitational wave interaction or emission. And there, of course, there's plenty of exotic models too, right? Like quark nuggets and boson stars, whatever. There's no shortage of things that are very exotic.
Okay, but mainstream answer is probably not. Thanks.
Mainstream answer, I think, is probably not, but yeah.
Cool. Okay, I think there's one question in the chat as well from David. I think a couple lines down about what is FRB electromagnetic emission mechanism, and is there a good reason why FRBs can be interpreted as plasma emission?
I don't know. Is this a question or an answer to a previous question? I can't try and read it on the fly. Okay, yeah. I mean, I think the what is the FRB emission mechanism? I think I touched on that, saying there's just many models. I'm not quite sure. Can you maybe go into more detail about what you mean by plasma emission?
Yes, well, plasma emission basically is the most common mechanism for generating solar radio bursts. Basically, you have an electron beam that moves with maybe 0.6 speed of light, and then you have basically Langmuir waves generated. And so the key feature is that frequency drops with time, likewise in your FRBs. Mm-hmm. For the reason that the emission frequency, which is the plasma frequency, is proportional to the root of the number density of electrons. So basically, as the electron beam moves to more dilute plasma, your frequency drops. And, this is, I mean, I guess the FRB people don't know the literature than the solar radio models. And I think what needs to be done, basically, a simulation of FRB, not in the solar context, but in the context of basically you need a relativistic beam emitting. So my follow-up question is basically, is there any way to have a proxy how density varies with distance along the propagation of the beam? So the actual local plasma frequency I'm talking about.
Yeah, I mean, so certainly, so the model you're describing, which I'm just not an expert enough on the high energy astrophysics to be to comment on super intelligently, but the model you're describing does share some features of this Brian Mesker model that has outward propagating, in this case not electrons but a shock in a synchrotron maser, but but many aspects of this are very key in that you're traveling through lower and lower density material that makes the frequency drop as a function of time. And stuff like that. So I would look into that model because I think it shares a few of the same features, but I don't know why I think your more analogous model to solar emission would I don't know if it would work or if it doesn't, or if it's been considered in the literature. It's just not up to date enough. Now, I will say that there is in the early days of FRB, of the FRB field, we had an FRB catalog. And then there was always this joke that there were more theories of FRBs than there were FRBs observed. And so a group of people in the field took that a step further and created an FRB theory catalog. So there is both a catalog of FRBs on the web, but also a catalog of theories about FRBs on the web. And you can search that catalog and see if your model is already there or not.
Thank you. That's a good answer.
Cool. Okay, I think we're
one more quick question.
Oh yeah, Bernard, go for it.
I just wanted to point out that the gravitational lensing of fast radio bursts will be a very interesting probe, especially of dark matter in the very low mass range, sort of 10 to the minus 6 to 10 to the minus 4 solar masses, which, that's not the mainstream view for the dark matter, but some people consider that possibility. So the fast radio bursts are going to be really interesting in that context.
Absolutely. And this gives me an opportunity to plug Kelvin Long. He works on the DLBI, but the other half of his time he works on the gravitational wave search, gravitational lens search in the FRBs. And he is giving a talk at APS this coming week It's a 10-minute talk. It'll be recorded. Like, go Google it. It has all of our forecasts and the current progress in the pipeline. That is very much happening. And you're absolutely right. This is going to be splendidly powerful for constraining 10 to the 4 to 10 to the minus 4 and up. I think solar mass black holes is dark matter.
Indeed, that's wonderful. And I hope there'll be a paper on that corresponding to the talk too.
There will be a paper. There is not going to be a forecast paper. There is going to be a search paper, but that requires us to complete the search.
Okay.
And there'll be a search paper, search and interpretation paper, and that takes time because we actually have to, open the box and look at all the data in a very careful way, which you might imagine is challenging.
Yep. Thank you very much.
Okay, Kiyo, once again, thank you very much for a really nice talk and a very long and interesting question and answer session. So thanks very much. So that kind of concludes the formal part of the seminar today. So thanks everyone for attending. We're gonna have sort of some social discussions for the next sort of 15, 20 minutes or so. So do stick around if you can. Otherwise, I hope you all have a great weekend. So, cheers.